Hello and welcome to our webinar on EV NVH. I'm Dave Bogema, Director of NVH Solutions at VI Grade. Today we'll be talking about EVs and how to engineer the sound of electrified vehicles to meet brand and customer expectations. To begin, I want to quickly define the types of vehicles we will be addressing today. I'm sure most everyone is familiar with the various types of electrified vehicle powertrains, but we're going to be broadly addressing hybrid vehicles, both general hybrid and plug-in, which typically have an internal combustion engine together with an electric motor, and fully electric vehicles or battery electric vehicles. I also want to take a few minutes and define what NVH is. NVH is automotive sound and vibration. NVH is one of the main attributes controlling and delivering vehicle refinement and brand DNA. Consciously or not, people make decisions and form opinions based on the sound and vibration they perceive from the vehicle. This includes powertrain sound and vibration. For EV powertrains, this mostly consists of tonal gear and motor noise, fans, and noise generated by power electronics. When we bring hybrids into the mix, we also have all the typical sound and vibration challenges inherent in internal combustion engines. NVH also includes road noise and vibration, from secondary ride to imbalances and structure-borne and airborne road and tire noise. Wind noise is another major component. And then we have anything and everything else on the vehicle that makes sound or vibrates: brakes, HVAC, chimes and warning sounds, and so forth. All of this falls under NVH. I want to emphasize here that sound covers a large portion of these phenomena, but vibration is also key to many of these, and there is a big overlap area here. Vibration is something we cannot overlook when talking about EV NVH. The perception of sound and vibration are inextricably linked together. Sound and vibration levels interact and affect the human perception of that sound and vibration in ways that are not always intuitive. The overall perception of the driver and occupants involves both sound and vibration as a combined quality. In EVs, the absence of engine vibration may now make other vibration sources more noticeable or objectionable. In hybrids, the vibration associated with the engine starting and stopping, or the intermittent or unpredictable changes in engine operating state and vibration, can directly influence the overall perception of sound and vibration. I think we've all observed that sales of EVs are increasing rapidly, and EV sales are projected to continue to increase substantially in the future. There are also many targets and commitments, both by governing bodies and by automakers themselves, to become 100% electrified or 100% EV or zero emission in the relatively near future. There are many challenges in EV NVH. First amongst them is the draining the swamp effect. Sounds traditionally masked by the engine are now more audible or more noticeable. And not just sounds, but vibration too. AC compressors or other ancillary devices on an EV can produce unwanted, unexpected vibration in the vehicle, most of which would never be noticed with an engine running. Another significant challenge is loss of character, especially for high-performance vehicles. How do we instill a sense of excitement? How do we make the emotional connection between the car and the driver now that we no longer have a combustion engine as the primary power source? There is legislation for minimum noise required for EVs and hybrids now. How do you meet those requirements and maintain or enhance brand image? Lightweighting is a topic that has been around for a while, and it is completely relevant today. Generally speaking, reducing mass means easier noise transmission and less mass budget for sound package material. We must meet the demand for increasingly better range and performance while maintaining the same or better NVH characteristics. Hybrid vehicles present their own set of challenges over and above pure electric vehicles. They have all the challenges of electric vehicles, combined with all the challenges of traditional IC engine vehicles, and a few more resulting from the combining of the systems. Autonomous vehicles provide an additional challenge. These provide a completely different occupant experience, where the occupants have more attention available to focus on the sound characteristics of the car, and whose expectations and desire for the sound character may be significantly different from a traditional driver-operated vehicle. Now, the final point, what should an EV sound like? There are probably as many answers to that as there are brands and models of cars. So the rest of this presentation is focused on how we discover, design, and deliver the right sound and vibration in the final production vehicle. We're going to take a look at how we evaluate NVH data. Many types of engineering data and CAE analysis can be adequately expressed, experienced, and understood visually. Decisions can be made by looking at a computer monitor. NVH data is a bit different. We get a lot of great information from testing, analysis, and simulation, but the results are typically in the form of plots and graphs. NVH data cannot be fully expressed, experienced, and understood by plots, graphs, numbers, and visual means. Numbers and plots and graphs are very useful, but they don't answer questions like, does it sound good? Or is it better than this other car? Or what does it sound like? To address this, we created our NVH driving simulators to enable the experience of all the various types of sound and vibration data together in an interactive, real-time driving simulator. Here's a short video overview of the NVH driving simulator solutions. Drive the future. Drive and experience the sound and vibration of vehicles interactively in a virtual environment. The best way to evaluate the NVH characteristics of a vehicle is to actually drive the vehicle. But what do you do when there is no physical vehicle to drive? How do you make NVH decisions with confidence? Whether existing vehicles or virtual prototypes, you can drive vehicles interactively and evaluate the sound of the vehicles just as you would drive a real car in a virtual environment. Evaluate vehicles back to back. Switch vehicles while driving. Easily compare the sound and vibration of vehicles for engine, electric motor, road, wind, or any other aspect or component. Capture customer preference. The vehicles driven in the simulator can be real existing vehicles, completely virtual vehicles based on CAE models and targets, or contain elements of both. The sound of the vehicle can be represented as several components, such as electric motors, engine, road, and wind sound, and can be further subdivided. These sounds can be derived from vehicle recordings or created from CAE models and data. The NVH simulator software is used to develop virtual vehicles and engineer new vehicle sounds. Apply filters and changes to the sound of the vehicle. Change the motor, gearbox, engine, exhaust, tires, and other components. The NVH simulator is the ideal environment for active sound design, designing and integrating electronic sound enhancement. There are several versions of the NVH simulator, all powered by the core NVH simulator software. The desktop NVH simulator is the primary workstation. The compact NVH simulator and static NVH simulator add vibration as well as sound. There is also the on-road NVH simulator and the exterior sound simulator. Listen to the sound of the vehicle before you build the car. Capture customer preference. Communicate design changes effectively and efficiently. Reduce the need for prototypes. Understand NVH data quickly and easily, and make decisions with more confidence than ever before possible. Drive, experience, understand, decide. The NVH simulator from VI Grade. That was a very brief overview of several solutions we can provide for NVH simulation. Today we're going to look at how these can be applied to electric vehicle NVH. The desktop NVH simulator enables us to drive and experience virtual prototypes and understand NVH in a natural way. Whether simulation data, measured data, or a combination of both, the desktop NVH simulator allows you to drive interactively, switch instantly back to back between vehicles or designs, turn on and off component parts of the sound like wind noise, road noise, and powertrain. Modify parts of the sound in real time with multiple types of filtering and sound modification tools. The NVH simulator software is at the core of all of the NVH simulator solutions and is used in all versions of the NVH simulator. There are more than 50 desktop NVH simulators installed at customer sites worldwide. Sound design is all about getting the right sound for the vehicle through the use of active sound design or electronic sound enhancement. The desktop NVH simulator is a big part of this solution, but so are third-party sound design tools. Together, you can design and tune the sound design of the vehicle in the correct context of all the other sounds of the car, including powertrain, road, wind, and other sources. You can tune the sound interactively over the full operating envelope of the vehicle. You can even take the sounds you design out in a real car for final evaluation and tuning with vSound or the on-road simulator. One such solution is the QNX LiveAmp software. LiveAmp is an advanced, full-featured, active sound design application integrated with the NVH simulator. Used together, you can easily design the right sound for your vehicle using active sound design and experiencing the results in the correct context of all other vehicle sounds interactively. Here's a brief video showing this in more detail. This is a demonstration of some of the sound design capabilities available within the NVH simulator together with the QNX LiveAmp software. Before I get started, I just want to mention the screen layout here is a bit more condensed than I would usually have it. I'm usually spread out on a couple of other screens, but today I've got everything kind of placed on one screen here. I'm also using the virtual driver controls rather than real driver controls because I wanted to be able to show you what I'm doing on the screen here. All right, well, let's get started. I'm going to start the car and pick one of my sounds here. I've got two active sound design sounds here. And so I'm just starting the first one here, and I can put it in gear and let's listen to what this sounds like. And you can hear that responds to the accelerator pedal. The sound changes as I speed up, slow down. Now I can turn that off. That's my sound design sound here. And then all you hear is the sound of the motor and the road noise. I can go the other way around too, or I could just turn off the motor so all you hear is the sound design. Or just the sound design by itself. And everything back together. All right, I've got another sound design sound here I'll play also. This one's quite sensitive to the accelerator pedal position. And then I can switch back to my other sound. So I can just switch back and forth between these back to back as much as I like. All right, let's take a look at the QNX software. So over here, I've got my QNX LiveAmp software up and running. And I'll give you a quick orientation to what you're looking at here. So we've got our design canvas here, and on that we've got several sound modules. And we've got lots of sound modules that we can use. So there's lots of different sources you can use here. So I'm only using some sine generators and a sample player here, but there's lots of different audio sources you can use. There are lots of filters you can use to shape that sound and lots of effects that you can apply to that. And even for each sound module, there's ways to modify that based on your input parameters. So here I've got my sine wave generator, and it's being pitch shifted here. I'm pitch shifting it based on vehicle speed. And each one of my sine generators has a different definition for that. I could actually tie that to anything. I could tie that to my throttle pedal. I could tie that to my motor RPM, load demand, whatever. I could make that dependent on anything. But these are all based on vehicle speed here. I also have my sample player here. So this is what is giving us kind of the real texture of the sound. And again, lots of different ways that you can modify this in real time. I'm also pitch shifting this based on vehicle speed, and this is something you can change and listen to right away. So any of these are. So I can, change how much I'm pitch shifting that. This is just the 0 speed pitch shifting basically. So I can move that around and hear that change instantly. Also, if you watch that yellow line, as I increase the throttle pedal and we start speeding up, that yellow line shows us what our vehicle speed is and the corresponding amount of pitch shift that's happening to our sound. I can also just turn this on and off. So I can just turn that off, and then all you hear are the extra sine waves that I'm adding in. I can turn that back on. So this gives you a lot of control over the sound, and it really gives you a lot of creative freedom to design the sounds that you need for the vehicle. I want to point out something else here too. Over here I have all my vehicle parameters over here on the right. And if I go over here and I press on the accelerator pedal, you'll see the throttle pedal and load start going up. You'll see the RPM and vehicle speed start going up. And as I pull back on that, you see those start decreasing. So the QNX Live Amp software is receiving these signals from the NVH simulator in real time. It then takes those signals, runs them through this, and generates the sound, and then we get that sound back in the NVH simulator, mix it all together with all the other parts of the vehicle sound, and play that out. So if we just have one more look at this, this is my first sound here. And I can just drive that completely interactively, and there's my second sound here. All right, well, this is a really basic introduction to sound design capabilities in the NVH simulator using QNX Live Amp. So I think you saw there how we can manipulate and design sounds in the context of the rest of the sounds in the vehicle. Now, let's move outside the vehicle. Everything that can be done for interior sound can also be applied to exterior sound. The exterior sound simulator enables the experience of the exterior sound of the vehicle under various operating conditions in the presence of different types of ambient noise and different levels of traffic, from the viewpoint of a stationary or moving observer. This is especially important for AVAS sounds. Exterior sound designs can be evaluated in the proper context of other vehicle sounds from tires and other sources, as well as various environmental ambient soundscapes. Here's a short video demonstration of some exterior vehicle sounds in the exterior sound simulator. I'm going to play 3 AVAS sounds first without any background noise. Now I'm going to turn on some ambient environmental noise. Now, hearing the sounds in the context of the ambient environment sounds makes a big difference. You could probably tell a difference in character as well as a difference in how easy it was to hear the sound and all of its component parts. With the exterior sound simulator, you can assess the exterior sounds of the vehicle in a variety of ambient sound conditions and even include varying levels of traffic with sound assigned to each traffic car. Like other versions of the NVH simulator, you can also adjust levels, apply filters, and switch back to back, all in real time. I previously mentioned that vibration was another important aspect of the overall vehicle experience. While we can do quite a bit of NVH design and evaluation on the desktop, for vibration we need a bit more. The compact NVH simulator enables us to experience vibration in the same way we use headphones to experience sound. The compact NVH simulator is the first simulator of its kind in the automotive industry. The key focus of this simulator is calibrated, integrated vibration and sound delivered in a system which can simulate any vehicle regardless of its inherent vibration characteristics and dynamic behavior. 7 independent degrees of freedom of vibration are delivered to the driver. Vibration is delivered to the seat in the vertical, lateral, and fore-aft directions. The steering wheel has vertical and lateral vibration components, and the footwell or heel point has vertical and lateral vibration as well. This combination delivers vibration to all driver touch points in the vehicle, providing a very realistic and accurate experience. Of course, the vibration is calibrated and equalized, so the exact vibration stimulus which simulates the vehicle is delivered to the driver. Sound is also a critical piece of the evaluation experience, so highly accurate, calibrated sound is provided through high-quality headphones and a subwoofer. It is really the combination of sound and vibration that delivers the unparalleled NVH experience. Anything we can do on the desktop, we can do on the compact simulator with the addition of multi-point calibrated vibration. For many years, we have offered the static NVH simulator, sometimes referred to as the full vehicle NVH simulator. Several of these have been built and delivered to customers and are in use today. Like the compact NVH simulator, the static NVH simulator adds calibrated, multi-axial vibration at all driver touchpoints, but built into the shell of a complete vehicle and surrounded by an expansive visual display. This is one of the most immersive ways to experience NVH data. At the heart of all forms of the NVH simulator is the NVH simulator software. This software is used in common with all versions of the NVH simulator, from desktop to the compact and the static, and even the on-road and exterior sound simulator. The same software and data models used on the desktop NVH simulator are used for the compact, static, and other versions of the NVH simulator. Subjective evaluation is a key component in deciding the question, what do people expect EVs to sound like? How do you really know what the perception, preference, or acceptance of your NVH design will be? With the NVH simulator jury software, you can present vehicle sounds and alternatives to evaluators with several methods for jury evaluation. Collect these results and process them to reveal insights into preference. The NVH simulator jury software can be used with any of the forms of the NVH simulator to gather subjective responses and understand the impact of your NVH designs. And it can be applied for a single evaluator driving the simulator or multiple evaluators simultaneously experiencing the same sounds and using the free iOS app to report and record votes. Especially important for EVs and hybrids is the ability to interface to external real-time performance models. Typically, a plant model exists for a vehicle which characterizes the vehicle performance. particularly when simulating different load splits between various motors and/or an IC engine, and in addition to taking into account battery temperature, thresholds of load demand, or charge level which cause the engine to engage for hybrids, and other factors, it is very helpful to have this external performance model able to be connected directly to the NVH simulator for more accurate NVH simulations. There are some basic performance modeling capabilities built into the NVH simulator software which enable driver-in-the-loop free driving, but for extremely accurate behavior, this software-in-the-loop connection to external performance models is very important. Provided with the NVH simulator software is a Simulink library, which enables very easy integration of Simulink-based models, but other real-time solutions can also be easily connected. Of course, the NVH simulator can utilize predefined operating conditions and maneuvers as well, where the vehicle speed, rotational speeds of motors or engine, driver load demand, load split between motors, and other factors are defined as a preset condition. Let's take a step back for a moment. For all disciplines and attributes, the traditional approach to designing a new vehicle has been to dream it, get an idea, then make it, build a prototype, then try it, drive it, see how it works. A much more efficient approach is to try it before you build it. Eliminate the wasted time and cost of building multiple prototype iterations. Simulate and experience the results of the simulation in driving simulators first, and iterate much faster than possible with traditional approaches. This is the overarching theme of everything we do at VI Grade. And this is the faster, easier, and safer approach to developing vehicles. CAE results and data are vital components of NVH virtual prototypes. We have worked together with several CAE suppliers to make it easy to bring CAE results into the NVH simulator and utilize these in virtual NVH prototypes. In fact, the NVH simulator is capable of easily accepting data from many different sources and in many different formats. Time data, frequency spectra, frequency response functions, and other data are easily utilized in the NVH simulator. The NVH simulator accepts measurement data from a wide variety of sources in all common file formats. Some data can be directly used in the simulator with no further need of data processing, but other data needs some preparation to be used in a real-time simulation. For example, test-based time data typically needs to be decomposed into its component parts. During runtime, the data is then not simply played back, but it is resynthesized in real time in response to driver inputs. This measurement data is decomposed using incredibly precise and fast time domain order extraction techniques to separate orders from masking. Data can be further processed to separate the masking noise into its component parts. When needed, the best-in-class time domain source path contribution software can be employed to calculate acoustic source strengths and mount forces and prepare complex source path contribution or transfer path analysis data for efficient modeling and playback in the NVH simulator. Experience over the last 20+ years of development and use and thousands of model builds have resulted in a set of tools which can handle virtually any data set and measurement situation when building NVH simulator models. When we talk about NVH simulator models, we can approach this at different levels of detail. Like any model, we only use the level of detail necessary for the evaluations and decisions that need to be made. Simple Level 1 models are very useful for benchmarking and high-level target setting and require very little time and data to create. In fact, you can create a simple Level 1 model that is completely functional for a driver-in-the-loop interactive simulation from a single recording. Models can also be more complex, moving to a Level 2 model where the sounds are broken into specific sources, especially for separating structure-borne road noise, airborne road noise, and wind noise. And moving to a further level of complexity, Level 3 models accommodate the need to predict and understand what impact specific components will have on the overall vehicle sound. Source path contribution concepts are intrinsic to the NVH simulator and NVH virtual prototypes. Source path contribution modeling is used to build up vehicle models from the component source level sound or vibration through the sound and vibration paths to the resultant contributions at the receiver location. The models can exist anywhere in between, matching complexity and capability to the need of the model. And again, any of this data can be real data measured on test tracks, measured in test rigs, or come from many different types of CAE models. Source path contribution modeling is a very important concept and fundamental approach. Powertrain, tire, and road forces, wind noise, accessories like AC compressors or heat pumps, and others are sources of noise and vibration. These sources all travel through various paths and end up as perception by the driver or occupants of the vehicle. The NVH simulator software enables you to build up the models in this way and control, modify, and monitor each piece of the source path contribution model. While NVH simulator models can be created entirely from measured data or entirely from CAE data, the vast majority of NVH simulator models and virtual prototypes are hybrid models of CAE and measured data. Often, test data will be used to provide context for components outside the scope of the immediate evaluation task, or for data in frequency ranges that are outside the scope of immediate evaluation and analysis. For example, say road noise is being analyzed. In this example, we have some data from the Altair NVH director, which is a combination of simulated loads at attachment points and transfer functions. A detailed finite element model of the vehicle and a high-quality tire model are used to generate road noise levels for the vehicle, but only up to about 200 Hz. This data can be accurately generated and played back in the NVH simulator, but listening to sound up to 200 Hz with nothing else above it is not that realistic. A good solution is to use surrogate road and wind data from a similar vehicle, perhaps even modified slightly to match future vehicle intent, and apply this above 200 Hz, while using the detailed analysis results below 200 Hz. In this example, we first hear only the CAE-generated data from 20 to 200 Hz. It doesn't sound very realistic on its own. Next, we add the surrogate data, filtered to include only data above 200 Hz. In this way, the sound can be presented as a complete, realistic road noise with the expected full band sound, which provides the proper context to evaluate the CAE data. This is a very basic example of hybrid test CAE modeling. There are many variations and ways this can be applied. Next, we're going to look at an example utilizing Romax spectrum to provide the EV powertrain forces and shell vibrations for the structure-borne and airborne source path contribution calculations. To illustrate how CAE can be used for powertrain sound quality, we're going to use this example, the Odin powertrain that Romax co-developed as part of a multinational R&D project. And to illustrate one of the key values of understanding powertrain sound quality before prototyping, we're going to compare two variants of this design, one based on an induction motor and one based on a switch reluctance motor. Induction motors are widely used, for example, by Tesla, and the technology is long established. Importantly, they are usually one of the quieter motor types. However, they also have a lower torque density and are harder to manufacture and can be less efficient than other motor types. Switched reluctance machines are robust and simple in design, making them easier and cheaper to manufacture as well as being very reliable. But they are harder to control and, critically for us, they tend to have stronger harmonic noise content, mainly due to higher torque ripple. So, we're going to look at the sound of both competing designs with an A-B comparison in a simulated driving environment with the NVH simulator. I'm going to show a couple of videos, one for the switch reluctance motor, one for the induction motor. Both are the same run-up in the same vehicle with the same road and wind masking sound. Here's the sound of the switch reluctance motor. And here's the sound of the induction motor. You could probably tell that the induction motor tones were less prominent and less obvious than those of the switch reluctance motor. A little post-processing reveals that the overall loudness of the tones of the induction motor are considerably lower than those of the switch reluctance motor. In the left plot, loudness is displayed in sones. For the first half of the run-up, the switch reluctance motor tones are about twice as loud as those of the induction motor. The tones generated by the gears are the same between the two motors, so the torque ripple and radial forces are responsible for the higher level of noise in the switch reluctance case. This is evident in the plot on the right. While the gear noise, the green and the blue lines, are the same for both the induction motor and the switch reluctance motor, and also the highest overall between the three types of forcing functions, the gear mesh, torque ripple, and radial forces. The noise due to the torque ripple and radial forces of the switch reluctance motor, the pink and purple lines, are much higher than that of the induction motor. At one point, around 40 kph, the torque ripple noise in the switch reluctance motor actually exceeds the level of gear noise. Again, I would highly recommend seeing the entire presentation covering this topic, available as an on-demand webinar on the Romax website. Another video presentation I would strongly encourage you to watch is the presentation by Chris Cundy that was given at the previous VI Grade virtual conference. Here, Chris reviews how the NVH simulator technology is used to make decisions faster and with more confidence when assessing powertrain NVH design decisions. He presents several case studies, including this one addressing electronic drive unit tonal noise. This is a case study of a small battery electric vehicle. As background, CE analysis indicated that the calculated forces from the motor would exceed the general target level, which indicates a risk of excessive tonal noise for the occupants. These calculated forces were used in an NVH simulator model, and it was possible to evaluate the design alternatives in the NVH simulator in the context of the rest of the vehicle sound. This made the decision to proceed with some design options and not others much easier to make. With the increased focus on EV development, we cannot overlook the fact that IC engines will be around for a while. Even by 2040, the prediction is that 50% of the vehicles sold will still have an engine, many of these in a hybrid configuration. Hybrids actually bring even more challenges to the table. Instead of just being the challenges of EVs or just the challenges of the IC engine vehicles, now we have to deal with both in one vehicle. On top of that, we have additional complications. Engine start-stop, sometimes at unpredictable times. Transitions between engine power and EV power. Power split issues. And in many cases, the engine in a hybrid doesn't respond to driver inputs the way an engine does in a traditional internal combustion engine vehicle. Any solution for experiential simulation must include a robust way to handle traditional internal combustion engine sound and vibration for real-time simulation. The VI grade NVH simulators have a long legacy of accurately simulating and generating engine harmonics and other engine sound and vibration phenomena, enabling the accurate representation of hybrid vehicles and all the phenomena involved in these. I also want to mention our engineering services. VI Grade can offer a wide variety of engineering services to help you in designing and achieving the right sound and vibration for your vehicle or product. Our engineering services team has a deep understanding of automotive sound and vibration from hundreds of projects conducted with automotive OEMs and suppliers. In conclusion, today we've reviewed the many challenges associated with electric vehicles and shown a number of examples of how VI Grade NVH simulator solutions can address these. VI Grade provides a complete, accurate, proven, and open set of solutions to enable you to design, simulate, and understand EV NVH challenges and solutions faster and accelerate product development. VI-grade NVH simulator solutions help you make better decisions faster with more confidence by bridging the gap between experience and simulation. That brings us to the end of our presentation. For a more in-depth look at the solutions you saw here today, contact us at info@vigrade.com. For more information, you can also visit us on the web or just scan the QR code on the screen. I would highly recommend watching the complete presentation from Romax and the full presentation of Ford's Chris Cundy on the real-world use of the NVH simulator. These are quite easy to find. Just go to www.vigrade.com/NVH, scroll down to the videos and webinars section, and you'll find the full Ford presentation there. And the easiest way to get to the Romax on-demand webinar is to go to the desktop NVH simulator page, scroll down a little bit to the video and webinar section, and it's right there. Thank you very much for your attention, and now I think it's time for any questions.